Far across the dark, a galaxy is drifting toward our own, and in 4 billion years, they will quietly become one. Andromeda, our nearest large neighbor, is moving through the silence at roughly 400,000 kilometers per hour, a slow and unhurried approach across an ocean of empty space. Tonight, as you rest, that approach continues, invisible, immense, indifferent to time. Two great spirals, each holding hundreds of billions of stars, are leaning gently toward each other, and somewhere in that distant future, the night sky as we know it will dissolve into something new. Welcome to Let's Learn While You Sleep. Tonight, we drift outward, past the warm, familiar Earth, past the pale moon, past the slow procession of planets, into a deeper darkness, where galaxies move like great quiet ships. Our destination is a story written across 4 billion years, the slow, inevitable meeting between the Milky Way, the galaxy we call home, and Andromeda, the brightest spiral in our night sky. This is not a tale of collision in the way we usually imagine it. There will be no fire, no shattering, no sound. Galaxies are mostly empty space, and when they meet, they pass through each other like two clouds of light, rearranging gravity, dancing, and eventually merging into something new. Tonight, you will rest while we trace this journey gently, through the structure of galaxies, the measurements that revealed Andromeda's approach, and the long, luminous future our descendants of starlight may one day inherit. Settle in. Let your breathing slow. The cosmos has all the time in the world. To understand what is approaching, we must first picture what we are. The Milky Way is a barred spiral galaxy, a vast rotating disk roughly 100,000 light-years across, holding somewhere between 100 and 400 billion stars. Our Sun is one of these, situated about 26,000 light-years from the galactic center, drifting through a quiet outer neighborhood on a minor spiral arm called the Orion Spur. From above, if any eye could see us from outside, the Milky Way would resemble a great luminous pinwheel, a glowing core wrapped in graceful arms, each arm threaded with dust, gas, and the slow nurseries where new stars are born. And yet most of the galaxy is not stars at all. The space between them is vast, almost unimaginably so. If our Sun were the size of a grain of sand, the next nearest star would be another grain of sand more than 6 kilometers away. Galaxies, despite their dense and glittering appearance, are mostly emptiness, a thin scattering of light suspended in darkness. Surrounding the visible disk lies a vast, invisible halo of dark matter, a substance we cannot see but whose gravity binds the galaxy together. This halo extends far beyond the bright spiral, perhaps 1 million light-years in every direction, a quiet gravitational presence shaping the motion of everything within. The Milky Way is not alone. It belongs to a small gathering called the Local Group, a collection of more than 80 galaxies bound loosely by gravity. Most are small, faint, and orbit the two largest members, like moths around a lantern. Those two great members are the Milky Way and Andromeda, sisters, in a sense, drifting slowly toward each other across the dark. Tonight, as you breathe, this enormous wheel of stars turns beneath you, carrying you patiently through the universe. You are already part of a journey older than the Earth itself. Now let us turn our gaze outward toward Andromeda. On a clear, dark autumn night, far from city lights, you can find her with the unaided eye. She appears as a faint, elongated smudge of light near the constellation that bears her name, a princess of Greek myth, daughter of Cassiopeia. For thousands of years, human beings looked up at this soft glow without understanding what it was. The Persian astronomer Abd al-Rahman al-Sufi described it in the year 964, calling it a small cloud. For most of history, it was thought to be a nebula, a patch of luminous gas inside our own galaxy. The truth would not arrive until the 1920s, when the American astronomer Edwin Hubble, using the Great Hooker telescope at Mount Wilson, measured the distance to certain pulsing stars within that smudge. His measurements revealed something staggering. Andromeda was not a cloud inside our galaxy. It was a galaxy itself, far beyond the Milky Way, an entire island universe of its own. With that single discovery, the known cosmos expanded almost beyond comprehension. The universe was no longer one galaxy. It was countless galaxies, scattered like seeds across an unimaginable distance. Today we know Andromeda lies approximately 2.5 million light-years away. The light reaching your eyes tonight from that faint smudge left Andromeda when our earliest human ancestors were just beginning to shape stone tools on the plains of Africa. It crossed an ocean of empty space for 2.5 million years, undisturbed, untouched, to arrive precisely at your retina. Andromeda is larger than the Milky Way, holding perhaps 1 trillion stars, possibly more. Her spiral is broader, her core brighter, and within her drift, many smaller satellite galaxies of her own. Across that vast, quiet distance, she is the closest large galaxy to us, our nearest sister in the dark, and she is coming closer. How do we know that Andromeda is approaching? The answer lies in the colors of her light. When an object moves toward us through space, the light it emits is compressed, shifted slightly toward the blue end of the spectrum. When it moves away, the light is stretched, shifted toward the red. This phenomenon, known as the Doppler effect, applies not only to sound, but to every wave in the universe, including starlight. By carefully studying the spectra of stars within Andromeda, astronomers can measure with remarkable precision how the galaxy is moving relative to us. As early as 1912, the American astronomer Vesto Slipher, working at the Lowell Observatory in Arizona, made the first measurements of Andromeda's motion. His results were striking. Almost every other galaxy he observed was moving away from us. Their light shifted toward red. But Andromeda's light was shifted toward blue. She was approaching. The measurements have since been refined many times. Today we know that Andromeda is moving toward the Milky Way at roughly 110 kilometers per second, or about 400,000 kilometers per hour. That is faster than any spacecraft humans have ever built. And yet, across the immense gulf of 2.5 million light-years, it is almost agonizingly slow. To know what would happen when the two galaxies met, astronomers needed something more. They needed to know not only how fast Andromeda was approaching, but in what direction exactly she was drifting through space. Measuring this sideways motion is extraordinarily difficult. It required decades of careful observation, and it was only in 2012 that scientists using the Hubble Space Telescope completed measurements precise enough to settle the question. The result confirmed what many had long suspected. Andromeda is not merely drifting past us. Her trajectory and ours are leaning toward each other. The two galaxies are on a course to meet. The encounter, when it comes, will be gentle in pace but utterly transformative. A slow gravitational dance written across billions of years. Imagine, then, the long approach. 4 billion years is a span almost beyond human comprehension. To measure it against something familiar, consider that our Earth itself is only about 4.5 billion years old. The time remaining before Andromeda arrives is nearly as long as the age of our planet. In that span, suns will be born and suns will die. Continents on Earth will rearrange themselves many times over. Life, in whatever form it takes by then, will have moved through forms we cannot imagine. And throughout it all, Andromeda will be drifting closer, almost imperceptibly, growing slowly larger in the night sky of any world that still has one. For now, she is a soft smudge, barely visible. But in about 2 billion years, halfway through the journey, she will have grown significantly, large enough to be clearly seen as a structured spiral, her dust lanes and bright core visible to any creature with eyes turned upward. By 3 billion years from now, she will fill a substantial portion of the sky, an enormous glowing presence brighter than the moon, suspended above the horizon night after night. And then, somewhere near 4 billion years from now, the outer edges of the two galaxies will begin to touch. Even then, there will be no flash, no sound, no sudden shock. Galaxies, remember, are mostly emptiness. The stars within them are so far apart that direct stellar collisions are vanishingly rare. Astronomers estimate that the chance of our Sun colliding with another star during the entire merger is essentially zero. Instead, what will happen is something far more graceful. The gravity of each galaxy will begin to pull at the other, twisting the spiral arms into long luminous streams, scattering stars into new orbits, igniting fresh waves of star formation as great clouds of gas are compressed by the encounter. The two galaxies will pass through each other once, drift apart, and then, drawn back by their mutual gravity, return for a second embrace, and finally a third, slowly losing their separate identities. Consider for a moment What will happen when the two galaxies first begin to truly feel one another? Gravity, that quiet sculptor of the cosmos, will reach across the shrinking distance and begin to pull at the outer arms of each galaxy, drawing long, luminous streamers of stars and gas into delicate, curving tails. Astronomers have observed this very process in other galaxies elsewhere in the universe, frozen mid-collision, their spiral arms unwound into glowing ribbons that stretch for hundreds of thousands of light-years. The mice galaxies, the antennae galaxies, the tadpole, each one a portrait of what awaits the Milky Way and Andromeda in the deep future. And yet, despite the grandeur of these transformations, despite the apparent violence of two great spiral cities being torn open, the stars themselves will almost certainly not collide. The reason is a matter of scale that the human mind can scarcely hold. Within a galaxy, stars are separated by such enormous distances that if you shrank the sun to the size of a grain of sand, its nearest neighbor would be another grain of sand resting roughly 7 kilometers away. Galaxies, then, are not crowded places. They are vast, echoing volumes of near emptiness, decorated with sparse points of light. When Andromeda and the Milky Way meet, their stars will pass through one another like two clouds of fireflies drifting through the same summer meadow, intermingling without ever touching. The gas and dust between the stars, however, will behave very differently. Those diffuse clouds, spread thinly across thousands of light years, will crash directly into one another, compressing, heating, and igniting bursts of new star formation. Astronomers expect that the merging galaxies will glow with vast nurseries of newborn suns, blue and brilliant, sprinkled throughout regions where before there had been only quiet drifting hydrogen. The collision, in this sense, is also a creation. Out of disruption comes light. Out of gravitational chaos, somewhere in that darkness, new worlds will eventually condense from the swirling debris, perhaps to be circled in time by new and patient planets. What of our sun then, drifting through this slow encounter? Where, in the swirling reconfiguration of two galaxies, will our small yellow star find itself? Current simulations, run on powerful supercomputers by teams at institutions such as the Harvard-Smithsonian Center for Astrophysics, suggest a range of possible fates. In some models, the sun is gently flung outward by gravitational interactions, carried far from its present orbit into the distant outskirts of the merged galaxy. In others, it drifts inward, closer to the new galactic center, where the combined supermassive black holes of Andromeda and the Milky Way will eventually spiral toward one another and fuse. The probability that our solar system will be ejected entirely into intergalactic space is small but not zero. The probability that any planet, including Earth, will be physically struck or dramatically disturbed is, by all current estimates, vanishingly low. The distances, again, are simply too great. And yet the sky above Earth, or above whatever world our descendants, if any remain, might inhabit, will be utterly transformed. For long stretches of time across the 4 billion year approach, Andromeda will grow larger and brighter until it dominates the night sky, a luminous spiral wheel sprawling across the heavens. Then, as the galaxies pass through one another, the night will become a strange and shifting tapestry. Bands of dust silhouetted against billions of distant suns, regions of brilliant new star formation glowing in soft pinks and blues, streams of stars curving overhead like rivers of light. In time, after several passes and counterpasses spanning perhaps another 1 billion or 2 years beyond the first encounter, the two spirals will lose their distinct shapes entirely. Their stars will settle into a great rounded swarm, a single elliptical galaxy, smooth and quiet. Astronomers have already given this future galaxy a tentative name, Milkomeda, or sometimes Milkdromeda, a name like a lullaby, a name for a place that does not yet exist, but waits, patiently, across an ocean of time so vast that our entire recorded history fits inside a single fading heartbeat of its becoming. There is something profoundly humbling about contemplating these timescales. 4 billion years ago, on the surface of our young Earth, there were no plants, no animals, no eyes to look upward at any sky. The oceans had only recently formed. The first simple, single-celled life was perhaps just beginning to stir in warm, mineral-rich waters near hydrothermal vents on the ocean floor. From that distant moment to this present night, an entire planetary biosphere has unfolded. Bacteria, then complex cells, then jellyfish drifting in ancient seas, then fish, then forests of strange tree-like ferns, then dinosaurs walking beneath a sky in which Andromeda was already approaching, though no creature on Earth could possibly have known. Mammals emerged, primates evolved. Eventually, somewhere along that improbable chain, a species arose that could measure the speed of distant galaxies by the colors of their light. Now consider that the same span of time, 4 billion years, separates us from the moment when Andromeda will finally arrive. Whatever happens between then and now, whatever rises, whatever vanishes, whatever inherits this small blue world, will unfold across a stretch of time equivalent to all that has already passed since life first whispered into being. The sun itself, by then, will have begun to change. Stars like our sun do not burn forever. After approximately 10 billion years of stable hydrogen fusion, they swell into red giants, expanding outward and shedding their outer layers in glowing veils. Our sun is currently about 4.6 billion years old, which means that by the time Andromeda arrives, the sun will be approaching the late stages of its main sequence life. Earth, long before then, will have become uninhabitable to life as we know it, scorched by a brightening sun whose luminosity grows by roughly 1% every 100 million years. And yet, even as our small world fades, the larger dance continues. Galaxies waltz across the void. Stars are born from the ashes of older stars. The universe, in its quiet, patient way, goes on becoming. At the very heart of each galaxy lies a supermassive black hole, an object of such density that not even light can escape its grasp once it crosses the boundary called the event horizon. The Milky Way's central black hole, known as Sagittarius A star, contains roughly 4 million times the mass of our Sun and was directly imaged for the first time in 2022 by the Event Horizon Telescope collaboration. Andromeda's central black hole is considerably larger, estimated at somewhere between 100 million and 200 million solar masses. When the two galaxies finally settle into one, these two enormous black holes will begin a long, slow spiral toward each other, drawn together by gravity and by the gentle friction of stars and gas swirling around them. Over hundreds of millions of years, perhaps longer, they will dance ever closer, their orbits tightening, until at last they merge into a single, more massive black hole at the center of Milkomeda. In that final embrace, ripples in the fabric of space-time itself, gravitational waves, will radiate outward across the universe, carrying the news of the union to any distant observers patient enough and equipped enough to listen. Such waves have already been detected from smaller black hole mergers, first observed in 2015 by the LIGO instruments, an achievement so profound that it earned the Nobel Prize in Physics in 2017. The wave from Milkomeda's central merger will be far grander, though by then there may be no one left in this particular corner of the cosmos to hear it. And so the long story continues, written not in words, but in motion, in light, in gravity, in the slow turning of vast luminous wheels across the dark. Andromeda is coming. It has been coming for longer than there have been minds to wonder about it. And tonight, somewhere above the quiet rooftops of the world, its light, 4 billion years before that meeting, slips silently down onto your eyelids as you rest. When these two supermassive black holes eventually find one another, perhaps a few 100 million years after the galaxies first merge, they will begin a slow gravitational dance that astronomers call a binary inspiral. They will orbit each other at first from a great distance, separated by light years, drawing closer over enormous spans of time as they shed energy into the surrounding stars and gas. Each passing star that strays too near will be flung outward, carrying away a tiny fraction of the black hole's orbital momentum. And in this gradual exchange, the two giants will spiral inward, century by century, eon by eon. Eventually, perhaps after another 100 million years, they will come close enough that a new mechanism takes over. The fabric of space-time itself will begin to ripple as they orbit, sending gravitational waves outward across the cosmos. Waves so faint that we can only detect their largest cousins with instruments like LIGO and the planned space-based observatory called LISA. These waves will carry energy away from the binary, drawing the black holes closer still, until at last they spiral together in a final crescendo that lasts only seconds. releasing more energy in that brief moment than all the stars in both galaxies combined. And yet, no one will be there to see it in any obvious way, for the merger will be hidden deep within the new galactic core, shrouded in dust and stars and the soft glow of an aging galactic center. The resulting black hole will be a single object, perhaps 200 million times the mass of our Sun, anchoring the heart of the merged galaxy that astronomers have already begun, half playfully, to call Milkomeda. From that moment onward, the new galaxy will settle into a slow, dignified middle age, its violent youth behind it, its great spiral arms unwound into a softer, more elliptical form. Consider, for a moment, how strange it is that we, here and now, already know the broad outline of this distant story, that we can speak of it with such gentle certainty, sitting beneath the stars of a planet that will be long gone by the time it unfolds. Yet, the merger itself, for all its grandeur, will be a remarkably peaceful affair from the perspective of any individual world. Galaxies, you see, are mostly empty space. The distances between stars are so vast that even when two galaxies pass directly through one another, the chance of any two stars colliding is vanishingly small, perhaps one collision for every trillion stars over the entire merger. If you stood on a planet orbiting some quiet sun during the height of the collision, you would not feel the ground shake, nor see stars whipping past in chaos. You would simply notice, over many human lifetimes, that the night sky had grown unimaginably rich. New constellations would emerge, drawn from stars that once belonged to a different galaxy. The Milky Way's familiar band would slowly twist and unwind, replaced by sweeping arcs of brilliance crossing the heavens in directions no ancestor of yours would recognize. Gas clouds, however, will not pass through one another so gently. Unlike stars, which are tiny points separated by oceans of vacuum, the diffuse hydrogen clouds drifting between the stars fill space more continuously, and when these clouds collide, they compress, they heat, they begin to glow. Across the merging galaxies, vast regions of compressed gas will ignite into bursts of star formation, lighting up entire spiral arms with the blue-white fire of newborn suns. Astronomers see this happening already in distant galactic collisions throughout the universe, in objects with names like the Antennae galaxies and ARP 220, where infrared light pours forth from countless stellar nurseries, triggered by gravitational interaction. Our future Milkomeda will likely shine, for a time, far more brightly than either of its parent galaxies, glowing with the warm light of perhaps 100 billion new stars born in the disturbance. And then, slowly, as the gas is consumed and the merger settles, this brilliance will fade, leaving behind a vast, smoother galaxy whose youthful exuberance has been spent. The age of bright star formation in our local universe, in some sense, will end with this final, glorious bloom. Consider what this means for the long arc of cosmic history. The Milky Way and Andromeda are the two largest members of what astronomers call the local group, a small gravitationally bound collection of roughly 80 galaxies, most of them tiny dwarf galaxies orbiting the two great spirals. When Milkomeda forms, it will dominate this little neighborhood almost entirely. The remaining dwarf galaxies, including the Triangulum galaxy known as M33, the Magellanic Clouds, and dozens of fainter companions, will be drawn into the new gravitational well one by one, slowly absorbed over billions of additional years. Beyond the local group, however, the universe will be growing ever more lonely. Dark energy, that mysterious force pushing the cosmos to expand faster and faster, is steadily carrying all other galaxy groups away from us. Already, the distances between galaxy clusters are increasing at accelerating rates, and current models suggest that given enough time, perhaps 100 billion years from now, every galaxy outside our own gravitationally bound local group will have receded beyond the cosmic horizon, their light forever stretched into invisibility. Any astronomers in the far future, looking out from worlds orbiting stars within Milkomeda, will see a strikingly different sky than the one we observe today. There will be no other galaxies visible to them. The vast cosmic web that we have spent the past century mapping, with its filaments and voids and clusters stretching across billions of light years, will have faded entirely from their view. Their universe, as far as they can see, will consist of a single great elliptical galaxy floating alone, in apparent emptiness. They may never know that they live in a universe of countless galaxies, that once there were neighbors, that once the night sky held faint smudges of light from worlds beyond their own. In this sense, our era, this strange brief moment when galaxies are still close enough to see one another, is a privileged window in cosmic history. We live, you and I, in the age when the universe is still revealing itself, when the evidence of its origins is still painted across the heavens. How did we come to know all this? It seems almost impossible that creatures bound to a small rocky world, living lives of perhaps 80 or 90 brief orbits around our local star, could have unraveled a story stretching across billions of years and millions of light years. And yet we have, slowly, patiently, through the accumulated work of generations. The first hint came in 1912, when an American astronomer named Vesto Slipher, working at the Lowell Observatory in Arizona, measured the spectrum of light from the Andromeda Nebula, as it was then called, and found that its light was shifted toward the blue end of the spectrum. This blue shift indicated that Andromeda was moving toward us, not away, an early clue that something unusual was happening in our cosmic neighborhood. At the time, no one even knew for certain that Andromeda lay outside the Milky Way. That mystery would not be resolved until 1924, when Edwin Hubble, using the Great 100-inch telescope at Mount Wilson, identified individual stars within Andromeda and used their pulsations to measure its distance, demonstrating beyond doubt that it was an entire separate galaxy, an island universe of its own. In the century since, astronomers have refined these measurements with extraordinary precision, using instruments aboard the Hubble Space Telescope and the European Space Agency's Gaia mission to track not just the radial motion of Andromeda toward us, but also its sideways motion across the sky. From these careful observations, current evidence suggests the collision is real, though its exact details, whether a direct hit or a more glancing pass, remain subjects of ongoing study. New data from Gaia released in recent years has even raised the possibility that the merger may be less head-on than once thought, perhaps a slower and gentler embrace than the dramatic collision envisioned in earlier models. The story, like all good science, continues to be written, refined, and occasionally revised. Yet the broad outline stands: two great spirals, drifting toward one another, destined to meet across an unimaginable gulf of time. Story begins, in a sense, with a young astronomer named Vesto Slipher, working in the high desert air of the Lowell Observatory in Arizona during the early years of the 20th century. Using a spectrograph attached to a modest telescope, he carefully measured the light coming from what was then called the Andromeda Nebula, and noticed something curious. The spectral lines were shifted slightly toward the blue end of the spectrum, suggesting motion toward us rather than away. This was in 1912, more than a decade before Edwin Hubble would prove that Andromeda was a separate galaxy entirely, lying far beyond the boundaries of our own Milky Way. Slipher could not yet know the full significance of what he had measured, but in that quiet observation, the first whisper of the coming collision had been recorded. Across the decades that followed, generation after generation of astronomers refined the measurements, adding new instruments, new techniques, new ways of seeing. They measured the radial velocity, the speed at which Andromeda approaches us along the line of sight, and found it to be roughly 110 kilometers per second. But this told only part of the story, because a galaxy might also move sideways, perpendicular to our view, and such motion is far more difficult to detect across such vast distances. For that, astronomers needed something extraordinary: the Hubble Space Telescope, observing the same stars in Andromeda over years, watching for their tiny apparent shifts against the more distant background of the universe. And in 2012, after careful analysis of these observations, a team led by Roland van der Marel announced that Andromeda's sideways motion was small enough that a direct collision with the Milky Way was essentially certain. Not a near miss, not a glancing encounter, a true merger. It was a moment, quiet and unannounced to most of the world, when humanity learned the fate of its galactic home. Written in the slow drift of stars across the night sky, decoded by patient minds across more than a century of careful watching. Consider for a moment what it means to know such a thing. To stand on a small rocky planet orbiting an ordinary star on one of the spiral arms of one of countless galaxies, and to have worked out, through mathematics, through light, through the patient accumulation of evidence, the fate of an object 2.5 million light-years away, billions of years in the future. There is something deeply humbling in this, and also something quietly magnificent. The universe, it turns out, is not entirely opaque to us. Its largest motions, its grandest choreographies, leave traces in the light that reaches our telescopes. And from those traces, we can reconstruct what was, what is, and what will be. And yet, for all our knowledge, the collision itself remains a thing of profound uncertainty in its details. Computer simulations, run on powerful supercomputers using the laws of gravity as we understand them, show us the likely shape of events. The long approach, the first close passage, perhaps 4.5 billion years from now, the tidal streams of stars pulled into great arcs across the sky, the second and third passes, and finally the merger of the two galactic cores into a single, larger system. Some simulations suggest the resulting galaxy will be elliptical in shape, smooth and featureless compared to the elegant spirals it came from. Researchers have even given this future galaxy a tentative name, Milkomeda, or sometimes Milkomeda, a small linguistic acknowledgement that the two will become one. But these are models, careful and educated approximations of what the equations predict. The actual collision, when it comes, will unfold according to physics far more intricate than any simulation can fully capture, involving dark matter halos, gas dynamics, star formation triggered by compression waves, and countless gravitational interactions between individual stars and clusters. Somewhere in that complexity lies the true future, waiting patiently across the vast distances of time, indifferent to our predictions, and yet, somehow, faintly illuminated by them. And so, far beyond your window, beyond the silent moon, beyond the distant planets drifting along their slow ellipses, two galaxies are leaning toward each other through an ocean of dark. There is no urgency in their motion. There is only the patient pull of gravity, the same gentle force that holds you to your bed tonight, working across distances no mind can truly hold. 4 billion years from now, in a sky no human eyes may ever see, the Milky Way and Andromeda will become one, a single great galaxy, slowly turning, full of stars old and new. Some astronomers have already given this future galaxy a name, calling it Milkomeda, a soft union of two ancient names. Tonight, as you rest, you carry within you atoms forged in stars that lived and died long before our sun was born. You are made of starlight. You are part of this slow cosmic story. Let that thought settle around you like a warm blanket. The universe is vast and unhurried, and you are gently inside it. Rest now, gently, knowing that the stars are still turning, the galaxies are still drifting, and tomorrow another quiet story will be waiting. Thank you for spending your night with Let's Learn While You Sleep. Subscribe and come back tomorrow night. We'll be here. Sleep well.